Hello? 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 Okay. Good morning, everyone. It's time to start. So let us continue with Stochastic machines. So in the last lecture, we introduced the formulation for soft SVM, which can account for all kinds of data, no matter if data is linearly separable or non-linearly separable, almost linearly separable, right? So we introduced slack variables to allow some examples to break into the margin, meaning that when we search for a linear classifier, we can exclude those outliers, right? We just maximize margin for the remaining points. And then we can simplify the objective function by removing those slack variables, and then we get our objective function. We usually call this objective function as the primal domain objective function. We'll explain why later. And then we talk about how to estimate the model parameters W. Here W is the augmented parameters, the weight vector. V is the bias parameter B, right? So correspondingly, the input vector or feature vector xi is augmented with constant 1, right? So I mentioned this many times just to avoid you being confused. So we talk about two commonly used framework to train SVM. One is called gradient descent framework. The other is called Stochastic gradient descent framework. Right? So it's basically almost the same steps as we did for linear regression, the least mean square regression. Right? You guys all have experience for this. Right? But here, to conduct stochastic gradient descent, we need to be careful. We need to be careful. That is, in each step, when we pick up a random example xi, yi from the current training set, you're going to need to repeat this xi, yi for big N times. So this big N is the size of training set. In other words, you're going to duplicate this randomly selected example to fit a data set. And this fit data set must be of the same size as original training set. So the reason is that we want to maintain the same kind of skills for the training loss and the regularization term as in the original objective. So you can see that in original objective function, you got two terms, right? One is regularization term, which encourages maximum margin, right? And the second is the training loss over the entire training set, right? So once you sample an example to calculate stochastic gradient, if you just calculate the loss for one particular example, you kind of mismatch the skew of the training loss, right? Compared with the original loss. That's why we need to duplicate this example multiple times, namely n times, so that your computed stochastic estimate of the training loss will match the same skew in terms of the training loss. Right? So, in more depth, we have provided theoretical analysis in our slides, which is just optional for you to read. So we can show that if you process your sample example in this way, the gradient you computed, this gradient is a stochastic gradient. Why? Because it depends on the random select example, right? So this stochastic gradient is an unbiased estimate of the exact gradient. That means if you take the expectation of the stochastic gradient with respect to the randomly sampled examples, they are equal to the exact gradient of the original loss. And this will guarantee that your stochastic gradient descent will converge to the optimum of your original objective function here. And more rigorous speaking, with probability 1. But you don't need to know why it is called with probability 1 almost surely, because it's kind of jargon from probability theory. Okay? So this is the only thing you need to be taken care of when you implement your own stochastic training for SVM. This is different from the least mean square, because least mean square, their objective does not contain any regularization term. So you don't need to intentionally fake the data set. And then we have finished the discussion about gradient descent and the stochastic gradient descent framework. We also got some experience in the least mean square regression problem, right? So I want to give a general discussion about the advantage and disadvantages of the two methods. So for the gradient descent framework, right, no matter what kind of objective function with which to optimize, you can imagine that each step of the update is accurate, right? Because you compute the accurate gradient. And the benefit is that, okay, my each update is effective and is accurate. So overall, I don't need too many steps to arrive at the function optimum. Like, suppose these are just the contours of the function values, objective function value. With the accurate update direction given each step, you might only need 10 or 15 steps to converge. That's the benefit of the gradient descent. Like, suppose your data set is not very large, and the cost to compute the exact gradient is not hard, it's not high, then you might prefer gradient descent. However, it will be too costly when the training set is too large. Like, suppose you have 1 billion training set, 1 billion training examples, right? So to compute the gradient of the training loss, you're going to go through all 1 billion examples, right? You need to calculate 1 billion times to get one gradient and perform one update, right? So that means, like, even you only need to perform 15 steps of gradient descent, you need to go through the whole data set 15 times, right? That's really costly. That's not favorable for the training set. And in this case, we would rather go with the stochastic gradient descent. So stochastic gradient descent is good at performing very frequent, much more frequent updates. Why? Because every time when we have an example, we immediately compute a stochastic approximation of the gradient, right? We use that stochastic gradient to update. Right? So you can imagine that given the 1 billion examples, you'll go through the training set once. You can update the model 1 billion times. That's really, really effective and efficient, right? So the problem is that every time your updating direction is really noisy, sometimes just incorrect, because it's kind of random, right? So take an analogy like running stochastic gradient descent, like a drunk driver to drive back home. Right? So I drive very fast, and but each step we just drive randomly, maybe north, maybe south, maybe southeast, whatever. But it drives very fast. And eventually, the stochastic optimization theorem tells us, even you do this random drive, you will end up with arriving at home finally. That's the benefit. Right? And when the data set is very large, stochastic gradient descent is always the favorable choice because the low quality of updates can be compensated by the high frequency of the updates. For example, given the same set of 1 billion examples, stochastic gradient descent is often observed to converge even before you have gone through all 1 billion examples. So that means you even do not need to finish one pass of this set, you converge to the function outcome. If you take a look at gradient descent, right? If you want to compute one step update, you need to go through the entire training set once, right? But of course, no gradient descent can tell you, okay, you only need to perform one step. You can arrive at the optimal of the function. So that's why in practice, stochastic gradient descent is always the more favorable choice for large data. Okay, any question so far? Yeah, and later we'll show some convergence results. You see that convergence rate of gradient descent is determined by the size of training set, but stochastic gradient descent is not. That's why when the data set is very large, you can see the convergence rate of gradient descent is really slow, but the stochastic gradient descent is much better. Okay. So now let us address the last technique in the stochastic training procedure for SVM. That is how to compute the stochastic gradient for the hinge loss. So actually we mentioned this problem in your last lecture, right? So this is our stochastic objective, right? So whenever we random pick up an example, we duplicate for big N times, we construct stochastic estimate of the training objective, which we call stochastic objective. Right? And then we calculate the gradient of this stochastic objective as our stochastic gradient. But there is a bottleneck here. The problem is that the hinge loss over this example xi or I is not differentiable. Right? It's a max function. It's a discontinuous function. So it's not differentiable. Now how can we get the stochastic gradient? Right? Without stochastic gradient, how can we update our model parameters? So to bypass this problem, we're going to use another concept called a subgradient or subderivative. Right? So we can view as a generalization of the gradient to non-differentiable functions. So optimization theory guarantees that even you update the model parameters along the subgradient, you can still guarantee to decrease the function and converge to the minimum or optimal of the function. Right? So now let us look at what's the definition of the subgradient. So remember, when we talk about the convex function, a nice property of convex function is that, okay, at any point, if you draw a tangent line of this convex function, which is the convex function is the blue line, and the tangent line is the red line, and the tangent line will stay below the entire body of the convex function. That's the benefit. That's the nice property of the convex function. So, and the slope of this tangent function is called the gradient of the gradient of the convex function, right? So, then what if this convex function is non-differentiable? Right? It is discontinuous and it does not have any gradient. But imagine we can still draw a line, right? Pass through some point, right? And then stay below the entire convex function body. So if we can find such a line, we call this line a subtangent line. And we take the slope of the subtangent line as our subgradient. Then we can use that slope to update our model parameters to minimize this objective function. If you concrete, we can take a look at this example, and this black curve, f of x, is convex for sure, right? As you can see, in most places it is differentiable, right? But at this particular place, x2 is not differentiable, right? It's not continuous. Remember, definition of continuous. Okay. The left limit must be equal to the right limit, of course it's not. Right? So at x2, f of x is not differentiable, but at x1, f is definitely differentiable. But for both points, we can still obtain a sub gradient or sub derivative. So let us first look at x1. Right? So at x1, we know the function value is f of x1, right? So we can easily draw a line, a tangent line, which passes through x1 and f of x1, and this dashed line obviously stays below the entire volume of f of x, right? So we denote the slope of this tangent line as g1. So g1 is the gradient of the function f at x1, and g1 is also called subgradient. Okay. Why? As long as you can draw a tangent line, pass through this point, and then stay below the entire function body, you can call it subtangent. So g1 is both the gradient and the subgradient at x1. Now I want to ask, at x1, how many tangent lines could I draw? Or how many subtangent lines could I draw? Any thought? Any guess?
I thought it was just one, but I'm not thinking about it, I guess.
You're right. Yeah, just one. So remember, if this function is differentiable at some point, well, you can only draw one tangent line. It's pretty easy to prove, but you need to sit down for 5 minutes. Right? So that means you only have one gradient or one subgradient. Now let us look at x2, right? We know x2, f at x2 is now differentiable, right? So now we can see we can draw quite a few subtangent lines, right? So like this line which crosses x2, f of x2 with slope g2, right? And this line with slope g3, right? So both lines stay below the entire function body, and of course goes through this point, right? Goes through this point of the function. Right? So both g2 and g3 are subtangent lines, and g2 and g3 are subgradients. Do we have any other subgradients at x2? Any thought? Yeah, right. Anyone would like to point out other choices of subtangent lines or subgradient?
Since if both of those are subgradients, would any possible line in between those two be a subgradient?
Yes, exactly, right? So actually you have numerous subtangent lines. Well, you can draw any line in between, right? In between two lines, pass through this x2, f of x2, right? They're gonna still stay below the entire function body. So there are valid subtangent lines as well. So there are slopes or valid subgradients. So you can see that actually when some point is not differentiable, you might have many choices of subgradient. You can pick up any one you feel convenient, you like it. Okay? So now go back to our hinge laws. Our strategy will be to compute the subgradient of the hinge laws. Like we use subgradient to update our model parameters. So this is a curve of the max function, while the x will corresponds to this function marker. Right? So of course you have a lot of choices of subgradient. Right? You're free to choose whatever you want, but here I just want to introduce a very convenient and very intuitive subgradient. Well, we're going to consider two cases. So first, if this hinge loss is 0, and that means the function value is here. And then I'm going to use this line, coincides with this horizontal part as the subtangent line. So remember, even this line coincides with horizontal line, still stay below the entire hinge loss function, right? So At this time, the subgradient will simply be 0. Why? Because this is just a horizontal line. Right? The 0 gradient. And then the subgradient for the whole objective will only be the gradient for the regularization term, which is W0. And we need to append 0. Why? Because the regularization term does not contain the bias parameter. Right? And the subgradient for the second term is simply 0. Because this corresponds to the subtangent line corresponds to this horizontal line. And the second case will be, okay, if this hinge loss is not 0, meaning that this 1 minus function margin is bigger than 0, and then we know that the function, function value will be here, right? So now I'm going to use this line as my subtangent line. And this subtangent line, of course, still stay below the entire maximum function, right? So we just calculate the gradient of this subtangent line as my subgradient, which is simply, now the hinge loss, the value will be 1 minus yi w transpose xi, right? If you take the gradient of w, will be simply minus yi xi, right? And of course, if you multiply the constant c and n outside, and combining with the gradient of the regularization term, you got the subgradient of the loss of the objective function in the second case, right? So it's just W0 pending 0 subtracted by the subgradient of hinge loss here. So now we can just plug in our computation of the subgradient into the stochastic gradient descent framework for SVM. Well, more rigorously speaking, this is called stochastic subgradient. It's not stochastic gradient because we actually don't have an exact gradient for the objective function that involves hinge loss. Right? So we're going to initialize all the model parameters at 0. So here, W0 is the superscript. Don't be confused at the subscript W0 here. Here, W0 is just the original feature weights, right? And then we concatenate with the bias parameter to get our augmented weight vector W, right? But here, W to the 0 indicates the whole model parameters values at a 0th step, right? And then we go through many epochs. Well, we need to set up the maximum number of epochs T, right? Inside each epoch, we're gonna randomly shuffle the training examples and then go through each training example xi by I. Then we update our model parameters W. W here includes both the feature weights and bias parameter according to the subgradient, right? And of course, we consider 2 cases of subgradients, and then this is just the condition to decide which case we fall in, right? Right? So this is the whole procedure. And if you in our next homework, you're requested to implement stochastic subgradient learning for SVM, I would like to recommend you to use this algorithm Taylor, right? So here again, the gamma t is learning rate, and it might have many tricks. We're gonna go to the setting of gamma t in a minute. Okay, so any question regarding this stochastic subgradient descent framework? Everyone's comfortable, right? Okay, so now let us talk about gamma t, right? The learning rate or the step size. So in our least mean square regression case, where we can simply set the learning rate to be a constant, small constant number, right? But in a more complicated objective function, if you really want your stochastic optimization procedure converges to the function optimum, you have to make some restriction on the learning rate gamma t. So here are the commonly used settings of gamma t that can guarantee your stochastic optimization reaches the function optimal with probability 1. Right? So what are these requirements? First, of course, the step size gamma t must be always positive. Right? Second, if you take the square of each step size, and then you sum over them from t equals 1 to infinity, then this whole summation must be bounded, meaning it's not infinite. And the third one is kind of like on the other side. If you don't take square, just add up all the step sizes from step 1 to step infinity, then this whole summation must diverge, meaning that the whole summation must be infinite. So, briefly speaking, this one is called square summable, and this one is called summation diverge. So what does it mean? Intuition is like this. So the square summable simply means your step size cannot be too large. Like if you take the square and you add them all together from their first step to infinite number of steps, right? This series must be finite. That just tells your step size cannot be too large. If it is too large, you can imagine it might perturbate forever and ever, fluctuate forever and ever, and then never stop at the function optimum. And then the second requirement, that is summation divergence, meaning that your step size cannot be too small. If you just add up all the step size together from step 1 to step infinity, it must be infinity. This is just to guarantee your step size to be enough large. Otherwise, you can imagine, okay, your step size decays too fast, and it will decay to 0 even before you arrive at the function optimum. So these two conditions actually expresses a trade-off between the two. Like your step size cannot be too large, your step size cannot be too small. That's the idea, right? Well, given those requirements, how do you show that your stochastic optimization converge the function optimum with probability 1? It's not the scope of this class. If you're interested, you can take a look at any optimization book. It will use a lot of techniques like series analysis and probability inequalities. You're welcome to read them. I read through them during my PhD study. But it's not the requirement of our class, just to give you a hint. Then someone may ask, right, what kind of gamma t can satisfy these requirements, right? So there are actually many. So here we give two common use schedules of gamma t. One is starting from gamma 0. Of course, gamma 0 must be cos t. Gamma 0 over 1 plus gamma 0 times t over a. So here there are two hyperparameters. One is a, one is gamma 0. You need to manually choose. And different choices of gamma 0 and a will affect your convergence rate and your learning curve, for sure. Another one is even simpler. You just choose an initial step size gamma 0, and then every time you just divide it by 1 plus t. Okay. It's easy to show both schedule of gamma t will satisfy these two conditions. Okay. And in the homework 4, you will be asked to tune this gamma 0 and a or gamma 0 to see how their choices will influence the training, stochastic training of SVM. Okay. So now, just to mention a little bit results to give you why stochastic gradient descent or stochastic learning is more favorable in the large data set. Right? So if our objective function is a strongly convex function, suppose we have big N examples, you have your input dimension, the feature vector dimension is D, right? So the number of iterations, if you want to reach an accuracy within epsilon, that means the distance between your learned model parameters and opt model parameters is less than epsilon. If you run gradient descent to reach such an accuracy, the number of updates will be big O times big O of n d logarithm 1 over epsilon. So you can see the number of the iterations required for gradient descent is dependent on the number of training examples. Okay? But for stochastic gradient descent, it's just d over epsilon. It actually does not. It is not influenced on the number of training examples used. So this actually gave a rigorous justification why we should favor stochastic learning in a large data set, because it doesn't care about the size of training set, the size of training data. Yeah, and SGD is generally preferable when the data size is huge. Okay. So far, any question regarding the stochastic training of SVM? Yeah, the last thing we want to emphasize is an interesting comparison to perception. So if we look at the framework for stochastic subgradient descent for SVM, you're going to go through each training. You're going to go through the data set for many epochs. Inside each epoch, you shuffle the training set randomly. Then go through each training example. You just look at which case your hinge loss will fall in, right? And then you update the model parameters according to the corresponding subgradient, right? So this actually very much resembles the perception update. Right? So if you still have the impression, or you're right now doing a perception homework, right? So this is the same framework, except the updating rule is changed, right? For the perception, we still look at the cases, right? If this product or function margin is less than or equal to 0, update W with this perception rule. Right? If this is bigger than 0, well, we don't update. That means our update, you can view as just add 0 to the current weight vector W, right? So now that the stochastic version for SVM, this kind of updates correspond to some subgradient of training objective, right? And naturally, people would ask, like, does the perception update correspond to another type of subgradient of the training objective? Right? The answer is yes. And it is not difficult to find that the perception update is essentially comes from the subgradient of this function. So basically, every time you meet the example x and y, right, I just calculate the subgradient of this max function. So you can check, right? So if this max function is 0, meaning that this second term is less than 0, right? And second term is less than 0, meaning that this y w transpose x, this product is bigger than 0, right? Meaning that, okay, we correctly predict example x. So you don't need to update it, because the subgradient is simply 0. On the other hand, if this max function is the letter, right, this minus y w transpose x, there's only one reason, that is this product itself is negative, right? If this part is negative and negative become positive, right? So you need to calculate the subgradient of this term, right? Which is y times x, right? This is y times x. So actually, when this term is less than 0, your subgradient of this objective is simply minus y x, right? And you update with stochastic. With the subgradient, you'll end up with the same rule, same update as perception update. Right? And if you contrast this to our SVM objective function, you'll find that it kind of like closely connected, right? So first, both of them use the kind of max function, right? But for SVM, we got a hinge loss. We have an extra term 1. Right, in the second item of the max function, right? And another difference is that for SVM we have extra regularization term, which is half W0 transpose W0, right? So it actually encourages the large margin classifiers, right? And as we discussed before, this regularization term penalizes a complicated hypothesis, right? Want to restrict your search space into a smaller subset of linear classifiers to reduce the visit dimension, to reduce the generalization error count, right? But for perception, you don't have this. Right? You only have a loss defined this way, right? So, therefore, from computational learning theory, we can now clearly see the SVM objective is more advanced, right? Because it contains an actual regularization term to favor simpler hypothesis spaces. Right? So now, I want to give a brief summary for SVM training in the primal domain. I will explain why it's called primal training very soon. So the goal is to minimize irregularized hinge loss, and we can solve it using stochastic subgradient. The benefit is it's very fast. The runtime does not depend on the number of training examples, and it has some outright comparison with perception algorithm. Similar framework, but with different training objective. Right? Of course, stochastic subgradient descent is not the only choice for training SVM. You have many other choices. People have developed like numerous training algorithms. For example, this dual coordinate descent approach is also very popular. And if you want to use a very efficient implementation of SVM, you can use the so-called leap linear, which is implemented by a professor at the Cornell University. Okay, any questions so far? Everyone's good? Great. Now, we're going to talk about the dual space of SVM. Well, I bet most of people who said they know SVM, they don't know what's the dual space of SVM. How to train on dual space, what's the meaning of supervectors. They have no idea about this. But this is actually I think the most elegant part of SVM, in my understanding. So, in the last topic about SVM, we're going to talk about what's the definition of supervectors, why they are called supervector machines. And to reflect this definition, you have to look into the dual space, the dual formulation of SVM objective. Well, to introduce the dual representation of SVM, we have to review several basic concepts in the optimization theorem. If you have never heard of them, don't worry. It's very basic. All you need to do is just follow notations. That's it. It's not like very hard to show anything. It's just a connection of a set of basic definitions. And then we'll give the dual representation of SVM objective function. When we solve the dual function, we'll get to know where the support vectors come from. And also, only with the dual form, we'll be able to extend support vector machines to nonlinear classifiers. This trick is called the kernel trick. Okay. So we're going to first introduce dual forms, support vectors, and then we should introduce a set of common used trick to extend linear classifiers to nonlinear classifiers by doing some feature mapping. Many of such feature mappings might be into an infinite dimensional feature space. In that case, you cannot do an explicit feature mapping. You have to leverage some computational trick. And then we're going to go through some commonly used properties of kernels, and then we'll directly apply kernel trick to get our nonlinear SVM. That's the most common used SVM in practice. Okay. The reason we talk about the dual form SVM is we want to enable SVM dealing with nonlinear classifiers, although it's linear classifier, right? So we actually have a very intuitive explanation of such kind of trick. Right? Some of you might have seen that in homework problems. Right? So that is, in the original feature space, suppose those data points are now linearly separable. Right? That's obvious. Right? See, an intuitive trick will be, okay, and I'm gonna construct a new feature vector, right? So this is our original feature vector in the two-dimensional space, right? And based on this x1, x2, I'm gonna construct a new feature vector, which essentially map the original input in a new higher dimensional feature space, right? And in this new feature space, those points reside in the new feature space. They are now linearly separable. And then we train a linear classifier in a new feature space, or in a map feature space. That's the idea, right? So, of course, people might be curious what kind of feature mapping should we choose, right? And how high dimensional space do we need for this new feature vector, right? So we're going to discuss about this when we talk about the kernel tree, right? The kernel tree, you will see like most commonly used and powerful kernel tree will map the features into an infinite dimensional space. That means you cannot directly compute this thing because it's infinite dimensional. So now, the pre-step, right? The very first step, we have to view our SVM objective function in another domain. It's called dual domain. Right? To introduce the concept of the dual domain or dual form, we're gonna talk about the general constraint optimization problem. Okay? So, of course, the soft SVM objective is just a special instance of this general constraint optimization form, right? So, in general, we assume we're minimizing a function f of x. Like, here, we don't assume f is convex, whatever. You can optimize whatever function you want. And also, the x must be subject to m constraints. Okay? So each of those constraints is represented by an inequality, like g1x less than equal to 0, g2x less than equal to 0, and gm of x less than equal to 0. So this g function, again, can be any function. It can be very nonlinear, very complex. Right? And this inequalities actually restrict the search space of x from which you're gonna minimize our objective function f. Right? So we call these g functions as a constraint function. So I believe everyone has learned how to optimize a function with equality constraint, right? Anyone still remember how to do that? I suppose all my constraints just the equality, like g1x must be 0, g2x must be 0, and so on. Right? If you have such equality constraints, how would you like to solve that? Anyone recall how to do that? Everyone forgot? First, there's calculus course. How to do that? You need to construct a Lagrange function, right? And just set the Lagrange function gradient to be 0 and solve that gradient to be 0 and solve it, right? So now we're going to go through a more general case. Suppose our constraints are represented by inequalities rather than equalities. And similarly, we can construct a Lagrange function. So the Lagrange function is a function of x and a set of Lagrange multipliers, lambda. Right? So for each constraint function, we introduce a Lagrange multiplier. So g1 we introduce lambda 1, g2 we introduce lambda 2, and gm we introduce lambda m. So our Lagrange function is defined as the original objective f of x plus a summation of those constraint functions multiplied with the corresponding multipliers, Lagrange multipliers. This is called Lagrange function. So a very, very important conclusion is that solving this constraint optimization problem is equivalent to solving a minimax optimization problem over the Lagrange function. And we just put an extra constraint that is the Lagrange multipliers are non-negative. And for simplicity, I'm going to put the constraint on the bottom of max. So this is a bi-level optimization problem. So in the inner level, given x is fixed, we're going to maximize this Lagrange function with respect to lambda. Of course, lambda must be non-negative. And then in the outer level, we minimize this Lagrange function with respect to x. So it's to solve a min-max problem. So here I want to emphasize, to solve a minimax problem is not equal to solving a minimization problem nor maximization problem. It's a minimax problem. But why this is true, right? Why solving this original constraint optimization problem is equivalent to solving this minimax? Where, remember, for x, you don't have any constraint. X is free now. You only put a non-negative constraint over the Lagrange multipliers lambda. But why these two are equivalent? Okay. Yeah. The reason is as follows. If we fix x in outer level, right, then in the inner level, our goal becomes maximizing the Lagrange function with respect to lambda, right? Of course, lambda must be negative, must be non-negative. Okay? So we can take a look at this maximum value of Lagrange function. So if this given x satisfies all the constraints in the original problem, meaning that g1x less than equal to 0, g2x less than equal to 0, and gm of x less than equal to 0, what's the maximum value of this Lagrange function with respect to lambda? Any thought? Remember, in the outer level, x is fixed, so x is constant now. So you maximize this function with respect to lambda, right? So now that we know x satisfies all the constraints, right? All those g x less than or equal to 0, right? So we know each of these terms is negative, right? So now I want to maximize the whole function. What values should lambda i's take? What values should lambda take?
0.
Yeah, 0, right? Remember, lambda I is not multiplied a negative number, right? Because x satisfies those constraints, right? And of course, I want to maximize the whole function. This whole function now is determined by lambda. I have to set lambda I to be 0, right? Otherwise, if lambda I is bigger than 0, well, you got negative number added into the objective. So if we know that optimal values for all lambda i's are simply 0, now we know the maximum Lagrange function is just the objective function, the original objective function, f of x, right? So we can see that in outer level, if we fix x, like remember in outer level we minimize x, right? So if we fix x and if this x happens to satisfy all those constraints, when you solve the inner maximization problem, it is simply f of x. Right? It's simply our original objective function f of x. And then what if this given x violates any of those constraints? What's the optimal function value when you maximize this? Suppose x violates the first constraint, meaning that g1x is bigger than 0. Right? And we know we multiply lambda 1 with g1x, right? And g1x is positive. And now we know lambda must be positive. Now we want to maximize this whole function. What kind of lambda 1 should we choose? This is a linear function with respect to lambda 1, right? Lambda 1 times a positive factor, right? Now, if I want to maximize this whole function with respect to lambda, I can choose lambda 1 to be as large as possible. I need to choose lambda 1 to be infinity. Why? Because I maximize this function. And I choose lambda 1 to infinity, g1x is positive, right? The whole product will become infinity, and then this maximization will give you infinity. Right? So that means if your x from the auto level violates any of those constraints, then you maximize the Lagrange function with respect to lambda. It will end up with infinity. Right. So remember, we're doing minimax. In the auto level, we want to minimize the whole value here, right? Of course, we do not want to get infinity. Right? Those x who leads to infinity in an inner maximization result will be excluded. We won't want that result. That is equivalent to saying when we solve this minimax optimization problem, we automatically search the Autohacks from the space where all those constraints are satisfied, right? Because for any x which do not satisfy these constraints, their inner level is infinity, right? And I want to minimize in the outer level. So those results will be excluded. Does it make sense? Right? It's just follow a simple, not simple, I mean, a kind of like logic. If you do some kind of reasoning, you get to the point. Let me emphasize this again, right? If I analyze this bilateral optimization, right? We can consider in outside, when we fix any x, what is the result of the maximization in the inner level, right? So for any x in outside, if it satisfies all constraints, it reduces to the original objective function, right? And then you just minimize over it is equivalent to minimizing the original function subject to those constraints, right? But if the outside x given violates any of these constraints, your inner maximization step will give you infinity. That's definitely not our optimal x, right? Because our optimal x should give a minimum of the Lagrange function. So that's why by rewriting it as a minimax problem, although we explicitly get rid of any constraints over x, solving this minimax optimization problem is still equivalent to minimizing f of x when x is satisfied all these constraints. So this is a fundamental concept in the optimization course. I mean, it's definitely not hard to understand, but if you still do not catch up at the point, I mean, just after class, look at the slides for 5 more minutes, you'll get it. And the benefit here is that if we write down the minimax optimization problem instead, right? So we at least from the surface we kind of like make x to be free, right? And our constraint is only to require those Lagrange multipliers to be non-negative. That makes that will make your analysis much easier. And following the same logic, it's very trivial to incorporate equality constraints. Meaning that, okay, you can imagine your constraints will be a set of inequalities plus a set of equalities. You can conduct the same procedure, introducing actual Lagrange multipliers for the equality constraints, and to convert it to an equivalent minimax optimization problem. But as to how to arrive at, I will leave it as an exercise because if you can finish that exercise, you will truly understand the whole logic here. Okay, so we focus on this primal form, right? But someone asked, what if we switch the order of min and max? So in the primal form, we do the minimax optimization of the Lagrange function. In inner level, we do the maximization with respect to non-negative lambda, right? In outer level, we minimize. Right? This is called primal form. And now, if we instead, in inner level, we minimize the Lagrange function with respect to x, then in the outer level, we do a maximization with respect to lambda. Right? So what's the relationship between these two optimization problems? So the second one is called the dual form. So you can see the dual form and primal form. It's just the switch of the order for min and max. The primal form is doing min max, and dual form is to do a max min. But the objective function is exactly the same, and also constraints are exactly the same. Nothing else changed. It only changes the order of the min and max. So now I want to ask you to guess, will the two optimization problems end up with the same solution?
Yes.
Yes? That's your intuition, right? Any other thought? Well, I hope that's true, but this is a little bit counterintuitive. This, although we simply switch the order, the solution of these two problems are usually different. It's not equivalent. In the general case, we won't say equivalent. But what's the general relationship between the dual form and the primal form? In general, we can show that for arbitrary constraint optimization problem, if you solve the dual form, you get optimal function value, and also you solve the primal form, you got optimal function value. Then the optimal value of the dual form is less than or equal to the optimal form from the primal form. In other words, solving dual form is really viewed as solving a lower bound of the primal objective. Well, this is not hard to show, but I'm going to skip it because it's not required. Just to give you a sense, if you're interested, again, we listed the proof details. You just combine a few inequalities together. You will immediately derive this result. But here's a nice property of SVM. For support vector machines, the dual form is equivalent to the primal form, meaning that the solution from solving the dual optimization problem is exactly the same as the solution from solving the primal form or primal formulation. That gives us another viewpoint to analyze the solution, or to solve, or to train SVM. Right? We can definitely estimate the SVM in a dual formulation of the training objective and see what we can get. This is our plan. Right? This is our plan. We want to look into the dual form of our soft SVM objective. We'll try to solve that, and we'll try to extract some kind of insights. Okay. So let us look at the primal form of soft SVM first, right? So we know that this is a typical constraint optimization, where our objective is the regularizer plus a summation over the slack variables, right? I mentioned that the summation of slack variables will encourage as few examples as possible to break into the margin, right? And C here is a hyperparameter which controls the trade-off between the two, right? And also to allow some example to break into the margin, we introduce for each training example 2 constraints, right? The first constraint is that you're going to have a non-negative slack variable. The second constraint is that your function margin is no less than 1 minus this slack variable ci. Right? So now we're going to use the general formulation to convert it into an equivalent minimax optimization problem. Right? You just follow the template we provided a minute ago, right? So we're going to construct a Lagrange function which is the original objective functions here, and then for each training example we have 2 constraints, right? So we're gonna introduce 2 Lagrange multipliers. So alpha I for the first one, and beta I for the second one. But for the standard formulation, as we just mentioned, right, we require the constraint to be an inequality left-hand side, right? So the inequality will be something less than equal to 0, and this something less than equal to 0. So mean that you have to revert the direction of the inequalities. How can we do that? We can just multiply minus 1 in both sides, right? And then we multiply those constraint functions with corresponding Lagrange multipliers. We get our Lagrange function, right? So it's extremely complex, but it's pretty straightforward application of the general minimax formulation we just introduced, right? So you can see that it's subtracted by beta I and ci. Beta I is the Lagrange multiplier for this constraint, but the constraint function must be something negative, something less than equal to 0. So you need to put minus sign in front of it, right? And also here is the same thing, right? So now we get our primal form, which is minimax of this Lagrange function, where our model parameters in the outer level would minimize with respect to model parameters, including the bias parameter B, the weak vector W, and also the slack variables ci. Okay. In the inner level, we maximize the Lagrange function with respect to the Lagrange multipliers, alpha i's and beta i's, right? So remember, we require the Lagrange multipliers to be non-negative. So now, we just switch the order of max min to get a dual form of our SVM objective, right? So, as we mentioned, for SVM, because the objective is convex and this is and satisfies the Slater's condition, or Slater's condition simply says that your physical region is not empty. I mean, there are some point in the interior of the physical region. Well, you don't need to know what does it mean for interior, but just according to the Slater's condition, we can show that solving this dual form max min is equivalent to solving this primal form min max. So now we want to solve this max min problem for SVM formulation. How to solve that? Again, we do not want to directly deal with this bi-level optimization problem because it's hard. So we're gonna simplify this. How can we simplify this? Remember, this is bi-level, right? So let us assume in the outer level, those alpha i's, beta i's are fixed. Then we want to solve this inner minimization problem. How can we solve this? How can we solve this inner minimization problem given the Lagrange multiplier is fixed in all side? As usual, we take the gradient, right? We set the gradient to be 0. That's it, right? So we got 3 types of parameters: the model, the feature weights, the bias parameter, and all the slack variables, the CIs, right? So just to take the gradient of the Lagrange with respect to each of them and set them to be 0 and see what we can get, right? So we take the gradient of the L with respect to W, right? So if we take gradient, you see, you look at which terms are related to W, the first regularization term and also the term in the constraint function, right? You can immediately get W equals to this summation of alpha I, yi, xi over all the training examples. Right? So W is essentially a weighted summation of the training inputs. Okay. and weighted by the Lagrange multipliers alpha i's. And then, if you take the gradient of L with respect to bias parameter B to be 0, there's only one term. That is the constraint inside the Lagrange multipliers, right, which contains B, and you end up with this equation, where the summation over all alpha I y i's is 0. And similarly, if you take the gradient of L with respect to the slack variable, you get alpha I plus beta I equals to C, right? So now we just substitute these results back to L. Then we got our minimum value of L, right? Given alpha i's, beta i's in all the level base, right? We have to solve the inner minimization problem. If you substitute them back to L and you get minimum value of L, it is a quadratic function. So you can try to do that. I highly encourage you to do that. It's just some algebraic operations. Right? It's hard, and summation over training example, summation over training example is just the double summation, right? And yi, yj times alpha I, alpha j, and the inner product between every pair of the training inputs x and xj plus the summation of y. But remember, when we solve this inner minimization problem, right, we also need to respect the other results from the gradient being 0. So that means when we simplify this problem, we also need to require the alpha i's and beta i's satisfy this inequalities, because those come from when we're solving the inner minimization step, gradient must be 0. Any questions so far? Or is everyone comfortable with this? It's just the kind of application of this operations, and just the calculate gradient and solve them to be 0. Okay, so now we can see by our simplification step, we can simplify this max mean by a maximization problem solely, but we need to account for actual constraints, right? So further, we can see that because those beta i's never appear in an objective function, right? And also we have a constraint about beta I, that is alpha I plus beta I equal to C, right? So from this constraint, we know beta I must be C minus alpha I. So if you want beta I to be non-negative, as long as you require alpha I less than C, right? So in that sense, we can just get rid of beta I. We can just replace this by an actual constraint, that is alpha I less than equal to C. That initially means that, okay, as long as I get a value of I can get a value of beta I, right, implicitly. So now we get our final version of the dual form, right? And here we take a minus sign in objective, so the maximization now becomes minimization. So we minimize the quadratic function, and then you respect the two actual constraints. First, the summation of alpha I by I equals to 0. Second, alpha I must be between 0 and C. Okay. So these are just by a set of derivations. Right? You get the dual form, which is max mean optimization problem. Then to further simplify, you fix the Lagrange multipliers in outside. You solve the inner minimization problem. You got the optimal value of the inner minimization problem, and then you convert it to a single level optimization problem. Of course, in the solving of inner minimization, you introduce two actual constraints. So now we reduce to the simplest form for the dual formulation of SVM, and then how can we solve that? So this is a classical convex objective function, which is called quadratic optimization. So you don't need to worry about how to solve that. Of course, we can solve it with gradient descent or stochastic gradient descent if you want. Here we just suggest you to use the off-the-shelf library, like in SciPy, in NumPy. You can solve that. You don't need to write hundreds of lines of code to solve that. So someone asked, why we do a series of like a mathematical game to arrive this and then call another library to estimate the alpha I values, right? That is Lagrange multipliers. Why should we do this? Right? As we will say, it will enable kernel tree and nonlinear classification in an infinite dimensional space. As we mentioned, like if you perform nonlinear feature mapping, if you want to get a very good linear separability in a high dimensional space, many of such kind of mappings are infinite dimensional. And you need to get rid of the explicit computation of infinite dimensional mapping. That's why we should look into dual space, which we're going to discuss right away. So, but before we talk about the kernel tree, we need to first address the issue, right? So in the dual form, after a bunch of simplification, derivation, all kinds of stuff, we only need to obtain optimal Lagrange multipliers alpha 1 star to alpha n star, right? Remember, for each example, we have two multipliers, Lagrange multipliers. One is alpha 1, one is alpha, one is beta, right? So now, after a bunch of simplification, right, in our dual form, we only obtain the optimal values for alpha, alpha 1 star to alpha beta n star. Then the natural question would be, how do we recover the optimal model parameters, WB, in the original space, right? That's the first question we need to address. To get an optimal W is pretty simple. Why? Because in our inner minimization problem, right? Remember when we fix any alpha and betas in the outside, this max-min problem, right? When we solve the inner minimization problem, we take the gradient of the Lagrange L with respect to W to be 0. We have already known that W is a weighted summation of the training inputs, and the weights are just alpha values, right? So now, given the optimal values of alpha 1 star to alpha n star, we can just get our optimal B vector, right? Just substitute those optimal alphas for alpha. This is relatively straightforward, but how do we get B? Right? This is a little bit unobvious. Right? If we look into the inner minimization problem, right? When we take the gradient, take the gradient of the L with respect to B being 0, you see that you don't have any equations which can help us to find optimal B. Why? Because B is linear with this Lagrange function, right? You take the gradient just to make this coefficient to be 0. Okay? There's no way for you to recover B from these equations. Okay? And how can you recover B? To recover B, we need to leverage another fundamental results in optimization, which is called KKT conditions. So KKT conditions plays a central role in the optimization. If you take any optimization course, they will tell you what are the KKT conditions. Right? So what are KKT conditions? Well, you can view them as a set of testing conditions bound to a particular constraint optimization problem. So suppose I have a constraint optimization problem. By the way, here we just restrict to convex optimization problem, namely all those objective function and constraints are convex, but there are general KKT conditions for arbitrary constraint optimization problem. So suppose I have a constraint optimization problem. My objective function is f0, and I have a big M constraints, which are represented by f of 1 x less than equal to 0 to f of big M of x less than equal to 0. Okay? And then associated with this constraint optimization problems are a set of testing conditions, which we call KKT conditions. So for any pair of x input to the objective function and lambda correspond to the Lagrange multipliers of those constraints, we can test if this x and lambda pair satisfy these KKT conditions. If they satisfy the KKT conditions, then we may end up with some conclusion, like you have found an optimal value or whatever. Right? So let's see what are the KKT conditions. Right? So first, it requires x satisfy all the constraints. Right? That's valid, right? If you want to conclude that x is a solution, right? You must ensure that x satisfies all the constraints. Right? Second, the Lagrange multipliers must be non-negative. And third one is interesting. The product between each Lagrange multiplier and the corresponding constraint function is 0. That's lambda m times f of m is set to 0 for every constraint, and from 1 to big n. And finally, the gradient of the Lagrange function with respect to x is 0. So this set of conditions are the KKT conditions. And the very important is this. That is the product between the Lagrange multiplier and the constraint function 0. This is called complementary slackness. So we're going to leverage complementary slackness and our intermediate results when we simplify the max-min problem to get an optimal B. So what's the usage of the KKT conditions? Suppose I got a pair of x and lambda which satisfy KKT conditions. What kind of conclusions can we draw? So here is our general results. Well, again, you don't need to know how these are proved. Just to give you a sense of why we can use them in this way. So the first one is concentration condition. If you can find a pair of x star and lambda star, right, which satisfy the KKT conditions, and then we can claim that x star is a solution to the corresponding constraint optimization problem. However, in general, this is not a necessary condition, meaning that there can be a solution of this constraint optimization problem which do not satisfy KKT. So KKT condition is just the sufficient conditions, meaning that if you can find a particular pair of x star and lambda star which satisfy KKT conditions, then you can claim, okay, your x star is the solution. But people may ask, like, when KKT conditions can also be necessary, meaning that as long as I got a solution, and then it must be consistent with the KKT conditions. The necessary condition holds when your constraints are simple, meaning that your constraint is kind of linear functions. If your constraint functions can be written as an equality in this way, ax subtracted by b equals to 0, you can see this is essentially a linear function, right? It's just a vectorization form of linear functions. And then KKT conditions are both sufficient and necessary conditions to justify the optimal value of your objective. So what's the usage of KKT conditions? If you take a look, our SVM objective function, if you look at the constraints, right, you can see that all those constraints functions are linear, right? They are linear in W, B, and C, right? So that means if you can rearrange them, it will satisfy this simple form, right? And as a result, the solution of the dual form or the primal form of the SVM must obey the KKT conditions. Right? Meaning that if you solve the dual form, right, These two form, you got lambda, you got W, you got V, they will all satisfy all those conditions. So now we can use those results, combine with our intermediate results when we do this inner minimization, right? Combine them together to infer the optimal value of the bias parameter V. Okay, we're gonna go through this detail next Tuesday.